Okay, so we're now recording. Welcome everybody to this One World ABC meeting. We're delighted to have Michael Gutman speaking today. So Michael is a senior lecturer at the School of Informatics at the University of Edinburgh, and he's done lots of work in likelihood-free inference and ABC, and also related topics like contrastive learning and density ratio estimation. So yes, Michael says his talk is not too long, so I don't know, Michael, are you happy to take questions as we go along, or would you rather wait till the end?
I think I can take them as we go, yeah.
Okay, yeah, so if you want to ask a question, you can use the chat or raise your hands, or Michael might also want to pause for questions at certain points. And with that, I'll hand over to Michael.
Okay, thanks a lot, Dennis, for the kind introduction, and also thanks for the organizing team to allow me to speak here. And thanks to all of you to come along. So my presentation is on neural approximate sufficient statistics. It's based on a paper that appeared at iClear this year, and it's with a number of co-authors, and really the first two authors, Yang Shi and Ding Huai, did the hard work, and they also contributed equally. So I would like to acknowledge them very much. Good. So the key messages of my talk are threefold. Namely, the first one is that you can think that sufficient statistics are information maximizing representations. Then this kind of perspective on sufficient statistics means that we can learn approximate sufficient statistics using estimators of mutual informations or their proxy quantities. And then I will show that we can use the learned statistics to boost the performance of Bayesian inference methods for implicit or simulator-based models, namely so ABC or likelihood-free inference. Good, so my talk has three parts. First, a quick background on sufficient statistics. I hope I don't bore the statisticians in the audience, but perhaps the mutual information perspective is new, or at least it's important for this talk. Then the talk and the paper make kind of two contributions. So the first is that we can use modern neural networks to learn approximate sufficient statistics, which might be interesting on its own right. And now, perhaps for the audience here, is perhaps more important is that we can use, or that we use this neural sufficient statistics to boost approximate Bayesian inference. Okay, so just to set up notation, let's consider a parametric statistical models where theta denotes the parameters and x is the data. So I use here just like a bold vector notation to denote the generic data. So it could be a time series, it could be multiple time series. So it's just the data that we are modeling. Now, as perhaps everybody knows here, a statistic is a vector valued function of the data. So the simplest example would be if we have n data points, x1 to xn, which would be x, then the sample average is a simple statistic. Now, there is an important result, namely that the statistic is sufficient for a parameter theta, if and only if the distribution P of x given theta factorizes into two terms, where u and v are two non-negative functions, and the first term only depends on x, while the second term depends on x only via t of x. So in a way, theta interacts with x only via t of x in this second term. So if we can write the model in this form, then this t of x is sufficient for theta. So let's have a look at the classic example where we have n IID observation of a Gaussian random variable where the parameter is the mean, and we would assume here the variance is known. So the joint can be written in this way, so the joint of x can be written in this way. And now if we just rearrange terms, we get the two functions u and v, where u here is this term, and v depends on the sample average or t of x. So it only depends on the sample average, so only on the sufficient statistics t of x. And indeed, theta also only enters in this second term that includes the sufficient statistics at t of x. So the intuition is that in a way the model parameters only interact with the data through the sufficient statistics, T of x. The second intuition is if we now consider theta to be a random variable, because of the factorization, is that we have this independence relationships down here, meaning that if we know T of x, then x and theta are statistically independent. Okay, so what is the consequence of the factorization for inference? So if the model can be factorized in this way, and now we consider x to be fixed, so it's a given value of the observed data, then clearly the log likelihood function is just given as here in equation 4, which means that to infer theta from the data x, we actually don't need to know x, but only the sufficient statistics T of x. So in the Gaussian case, this would mean that actually don't really need to know all the data. It's sufficient to just know the sample average if we want to infer the mean for a known variance. Of course, and perhaps important for this audience, the sufficient statistics always a matter for Bayesian inference, just really because of the factorization, namely the posterior theta given x is equal to theta given s of x, or T of x here, if I have a typo, so the sufficient statistics T of x, and it's then just the product, what's proportional to the product between the prior and this function v, where here we should have a T instead of a s. Okay, so this may be all well known. So just briefly, why are the sufficient statistics important in practice? Perhaps one is that we actually don't need to access or store the raw data. It's sufficient to just store or work with the sufficient statistics, which is often much easier. So in the Gaussian case, this would mean you actually only need to store one number instead of n numbers. Now, for us in approximate Bayesian inference, what it means is that actually, rather than having to compare x and x prime, which is often very hard because of the high dimensionality, we only need to compare a T of x with, say, T of x prime, where x prime is just another data set or data point. And if indeed T has lower dimensionality than x, which we would hope is the case, then this comparison is much, much simpler. Okay, so now let's look at another characterization of sufficient statistics, namely one in terms of mutual information, which is important for this talk. So the mutual information between two random variables, here y1 and y2, is defined to be this expected log ratio between the joint and the product of the marginals, of the two marginals, p of y1 and p of y2. And a well-known result from information theory is the data processing inequality. So if we have a Markov chain, as here, where we have some random variable theta that produces x, and then conditional on x, we sample or produce another random variable z, then the mutual information between theta and z, so the z at the end of the chain, is always less than or equal than the mutual information between theta and x. So this means that we can't gain mutual information, but only actually lose it by transforming data. And while here we would typically think that we have a stochastic relationship between x and z, this inequality also holds for deterministic transformations, where z is just a function g of x. So whilst generally we have an information loss when we transform x, and we don't have an information loss if we use sufficient statistics. So we have this characterization of the sufficient statistics here in equation 9, namely that T is a sufficient statistics if and only if the mutual information between theta and T of x is equal to the mutual information between theta and x. And this is a kind of a key relationship for my talk. Okay, so much on the background on sufficient statistics. So now in the next part, we look into how we exploit this link between mutual information and sufficient statistics. Yes, so we have seen this characterization of the sufficient statistics in terms of mutual information. So because of the data processing inequality, right, we have also seen that actually, well, that this inequality in equation 11 holds, namely for any deterministic or other transformation G of X, we have that the mutual information between theta and the transformed data is less than the original mutual information between theta and X. So this immediately then leads to a variational characterization of the sufficient statistics as shown in equation 12 here, namely that T is a sufficient statistics if and only if indeed this equality here holds, namely if we search in a sufficiently large function space with this calligraphic G and maximize the mutual information between theta and the transformed data, the quantity or the function G that maximizes this mutual information is then equal to the sufficient statistic. And this is the key quantity that we will be using in our work. Of course, in practice, quite often we have to choose some kind of family of functions that we work with, and this will introduce an approximation. In our work, we work with neural networks with a fixed number of outputs. And this is kind of a key open question, perhaps already, namely, rather than simply fixing the dimensionality of the output of G, so the space wherever G maps X into, so the number of statistics, rather than fixing it just to 2 times the number of parameters, one may want to learn the dimensionality or do something smart there. Good. So maybe I can quickly pause and ask if there are any questions before moving on. I guess not, at least the system doesn't tell me so. So then let me continue with the statement that, well, estimating the mutual information is actually very hard. So the question is actually, well, how can you actually use this relationship here in practice if estimating the mutual information I is very difficult? So perhaps one thing that helps is that we are not really interested in the precise value of the mutual information, but rather in the transformation G that achieves the maximum of maximum mutual information between theta and G. So this can help, and we think that, well, this helps, and this is a bit an informal statement, because it broadens the set of applicable mutual information estimators to include also surrogate quantities, where just the argmax correlates well. So the argmax of the surrogate quantity correlates well with the argmax of the actual mutual information. So we'll be using 2 in this presentation, namely one that rather than using the KL divergence between the joint and the marginals in the characterization of mutual information, we use the more robust Jensen-Shannon divergence. So there has been some empirical work that the argmax of the JSD correlates well with just the argmax for the KL. So it's more, I think, empirical work. The second quantity that we'll be knowing is like the other perspective of what mutual information is. So rather than just the KL divergence between joint and marginals, the mutual information is also a nonlinear dependency measure. And so what we can here do then is use other nonlinear dependency measures. And we used the so-called distance correlation that was proposed a number of years ago in the annals of applied statistics. Okay, so I'm going to now to explain both approaches, namely the one with the JSD and the one with the distance correlation. So for the JSD, we'll be using yet another variation formulation, namely the variation formulation of the JSD as given in equation 13, namely that the JSD between the joint between theta and X and the product of the marginals is given as the solution to this optimization problem here in equation 13, where F is kind of a nonlinear function. that in the first term here takes theta and x as input coming from the joint, while here taking also theta and x as input, but the data comes from the product of the two marginals. SP here denotes the soft plus function, meaning the logarithm of 1 plus the exponential transformation. So what this then means is, well, we automatically get an objective for learning sufficient statistics by introducing here the function g that acts on the data x. So rather than having x here, we have here g of x in both terms. So member in the audience who are familiar with the literature may immediately recognize a link to ratio estimation and contrastive learning, because indeed solving equation 13 and also 14 really is the same as learning the ratio, really the log ratio between the joint and the product of the marginals by logistic regression. And in equation 14, what we would do is we put it in a particular constraint on how we process x. In particular, rather than kind of allowing x and theta to interact immediately, as perhaps in equation 13, what we do in equation 14 is theta is only allowed to interact with x via the transformation g of x. And this is really the key thing that then we have also seen in the characterization of the sufficient statistics, that theta only interacts with x via the sufficient statistics. Yeah, and we have used this kind of ratio estimation approach or contrastive learning approach some years ago in likelihood-free inference. Great. Okay. Moving on to how to learn sufficient statistics via distance correlation. So here I briefly introduce what the distance correlation is. So now theta and x are, well, we want to compute the distance correlation between theta and x, and R2 is defined, or the distance correlation, squared distance correlation is defined, no, actually just the distance correlation is defined as in equation 15 here, where in the numerator we have like the product between two random variables, a theta and ax, while here we normalize by in a way that by their standard deviation. So you can immediately think that actually if a theta and ax are just theta and x, then this is just a normal correlation coefficient. So, however, what is now ax and equivalently a theta? So it's the double-centered distance function. So we would use x and an x prime, where x prime comes from the same distribution as x, and then we double center it. So we normalize it here by the average distance for a given x prime. Here the same for a given x, and then we have to add back the average where we take the expectation both with respect to x and x prime. So the expectation here in the numerator in equation 15 is taken with respect to four random variables, namely respect to x and theta, namely their joint, as well as the independent and identically distributed tuple x prime and theta prime. And in the denominator, we take the expectation with respect to their margins. So this is like one definition of the distance correlations. There are also other ones, equivalent ones in terms of characteristics functions, and also something called the Brownian distance covariance. So I refer here the audience to the original papers. There are also strong links to the maximum mean discrepancy as in the reproducing kernel Hilbert space literature, which has been established also a number of years ago. So what is important for us is that, well, it has a number of key properties. Namely, first of all, its R is between 0 and 1. where 0 is equivalent to theta and x being independent, while a value of 1 means that theta and x are a linear transformation of each other. So this really makes it a nice nonlinear dependency measure between theta and x. What we do to learn approximate sufficient statistics is rather than working with x, applying here a function g on x and then maximizing the R2 value with respect to g. So compared perhaps to the JSD, here we only need to train one neural network. So G is here again a neural network. So we only need to train one rather than two, as it is in the JSD, where in the JSD, the second neural network was the function f here. And this makes it like overall just a faster method. Okay. I'll now move on to how we use these ideas of learning approximate sufficient statistics in order to boost Bayesian inference with implicit models. But maybe I pause again to ask whether there are any questions. I think I don't see any, so I will just continue. Okay, so what is the goal? So the goal is to do approximate Bayesian parameter inference for implicit models, where indeed with implicit models, I mean like simulator-based models or just models where we can sample from, but where evaluating the likelihood function is, for whatever reasons, computationally infeasible or highly impractical. So the overall approach is that we use these ideas that I've explained just before to learn approximate sufficient statistics that I denote here by S, and then aim at estimating P of theta given S, where S is just the extracted sufficient statistics, rather than aiming at learning or estimating P of theta given X. And this, the purpose is really to increase the efficiency. So in our work and the presentation here, we focus on sequential inference methods, and namely two that are quite different. So the first one is a variant of SMC ABC, so a classical method from ABC. While the second method is sequential neural likelihood, which is a more modern like machine learning based approach to do likelihood for inference. And we chose these two kind of methods because to illustrate that the approach is applicable to like a wide range of methods. So we don't think these like SMC, ABC, or SNL are the only two methods where we could use our approach. They are just really representative members of two large approaches to approximate Bayesian computation. Okay, so what is the general idea? So, well, there may be two general ideas. So the first is the sequential approach, and the second one is how we embed the learning of the sufficient statistics into it. So let's perhaps start here on the left top corner, where P of theta, it doesn't denote the prior, but just some kind of proposal distribution. So then, as that's typically in ABC or likelihood for inference, we generate some parameters from the proposal distribution. We use the generated parameter to generate some data. And then what is new is that we use theta and x to learn this statistics network, as I explained in the second part of my talk. And we do that while we also learn the posterior. So let's now think that we have a network that extracts a statistics, and we denote here S, the statistics is S of X. And now we use S, and together with the generated theta, in order to approximate the posterior, where this block here could be the SMC-ABC algorithm or, for instance, a sequential neural likelihood algorithm. So the point is then that we indeed estimate here the posterior of theta given the value of the sufficient statistics or the learned statistics of the observed data rather than just the raw data. Now, in order to close the loop in the sequential approach, is that this estimated posterior then informs the choice of the next proposal distribution. And then we go around learning both the sufficient, this network for the sufficient statistics, as well as the posterior. Okay, so that's kind of the bird's eye view. So what does it mean in terms of algorithms? So this is perhaps a little bit an ugly slide, but let me just work you through it. So this is the algorithm for a variant of SMC-ABC, where we use the neural sufficient statistics, and we denote it by SMC-ABC plus. So everything starts with our proposal distribution P1 that equals the prior. Then this block is, as I just explained, the standard thing that we would do in ABC. We just generate parameters from a proposal and then pass it through the simulator to generate data. Now, the main point is that we used generated data to learn approximate sufficient statistics. Then we proceed as usual is in SMC-ABC, namely we extract the sufficient statistics, so we pass the observed data X naught through the learned network to get S naught here, as well as the simulated data. We sort the generated like statistics according to the proximity to the observed statistics. And then we use, well, kind of the top M, say, parameter values. So those parameters for which the statistics is closest to the observed one. To fit like either a surrogate model or in standard SMC-ABC, we would just retain those parameters. So in a sense, here in our work, we fitted a surrogate model. So that's why I call it here a variant of SMC-ABC. In particular, we fitted a copula model. Let's denote that by P of theta given S naught. Now, because we used the proposal distributions and actually all the data from the previous round to fit this distribution, what we need to do is we need to correct via the importance weights that are here. So we have to divide by the mixture distribution of all our proposal distributions and then multiply in the prior. This is kind of like the same what we would do is in SMC-ABC. So rather perhaps than working here with a fitted model, we could just retain weighted parameters where the parameters are just weighted here by the importance weight. Now, how do we use the update or the posterior to inform the next proposal distribution? Well, in this work, we just set it to be equal. So the next proposal distribution just equals the learned posterior. And then we do that all rounds, and at the end, we just return the approximate posterior at the final round, or the weighted samples as our approximate posterior. Okay, in SNL, we do essentially a very similar thing. So we also generate here the data. We learn the approximate sufficient statistics using, again, all the data from all the rounds. We extract the summary statistics, so the learned statistics from the raw data, both for the observed and the generated one. And then, rather as in the previous slide, where we took like the SMC-ABC approach, we now take the sequential neural likelihood approach, where we fit a likelihood model to the data, which in the original work was a neural density estimator, namely a masked autorecursive flow, and in our work we do the same thing. Then we plug in the observed value of the learned approximate sufficient statistics to again obtain a surrogate likelihood function, multiplying in the prior, and we get a quantity that is proportional to the estimated posterior. And again, this estimated posterior will be the proposal distribution in the next round. So we do that all times, and then at the end, we turn the estimated posterior in the last round as our final estimate. Good. So much about the methods. So let's have a look at results. So the first result is, let's have a look at some examples. So the first one is quite a simple one, namely the Ising model. And here we use the JSD to extract or learn the approximate sufficient statistics. So the data is 64-dimensional. Our parameter is just one, namely theta, which is the coupling strength in the Ising model, and we have like a uniform prior. So we use this model because the sufficient statistics are known, so that we can obtain a reference posterior by rejection sampling. So let's have a look at the results shown in this figure. So here are the rounds. We have like 10 rounds in total. The quality of the fit is measured as, again, the JSD, but now the JSD between the approximate posterior and the reference posterior. So in blue, or in cyan, we have the standard like SMC ABC algorithm with our modification, where we use like a coupler model. And in red, we have the results of standard sequential neural likelihood. So black and pink here shows what we get by using exactly the same algorithms, but the learned sufficient statistics using our approach. And we can see that actually immediately, even after 2 rounds already, we have massively improved in terms of accuracy of our estimated posterior. And then actually we don't really improve much more via the multiple rounds afterwards. So here on the right-hand side, we make a comparison between the learned sufficient statistics using our approach and another approach that is very often used in ABC, namely where the posterior mean is taken as statistics. So there, what one would do is one would also generate data, but then perhaps learn a regression model, learning to predict theta from X, and then perhaps using deep neural networks again, or like just linear regression, and use then the learned network as proxies, as statistics. So what we here see is that, like on the x-axis is the sufficient statistics, while here we have the 2 learned neural statistics. So we see that if we target the posterior mean, we have like a large area where actually the neural stats doesn't really change as the sufficient statistics changes. So we there lose like resolution, which then indeed makes the posterior mean approach suboptimal. On the other hand, in the proposed approach, what we see is like an affine relationship between the learned statistics and the true sufficient statistics, which then indeed boosts performance. Let's have a look at another example, namely the Ornstein-Uhlenbeck process, where we just used a simple Euler-Maruyama method to discretize the system. So then we have like this autoregressive model in equation 18 and 19, where we update the value of x at time t just by this increment, delta xt, which has this nonlinear relationship between the parameters and the increment. And then we add here some noise and data. This is like a time series model, and the data, an example time series is shown here. So we have here 2 parameters, theta 1 and theta 2. So theta 1 here and theta 2 here, and we put uniform priors on them. Okay, so on the left, we show again the accuracy of the learned posterior versus the number of rounds. It's using the same color code. So SMC here in blue and SMC plus, where we use our learned sufficient statistics in pink. And we see that, that indeed we kind of more quickly converge to a better estimate of the posterior, while at the end, perhaps the results are quite similar. Perhaps the difference is even bigger for SNL, where indeed, again, very quickly, just from the beginning, we achieve much better performance than the original algorithm, where the only change, again, is just the use of the learned sufficient statistic. We have here some examples plots just to give you a flavor of how the learned posteriors look. So we see that using the sufficient statistics kind of corrects some kind of distortions that we may have in our estimated posterior, and the same really again for the SNL, which I think makes sense because indeed the statistics kind of extract structure from the data. Good. So so far we have just used like two proxies for the mutual information, namely the Einstein-Shannon divergence and the distance correlations. But our approaches allow us to use other kind of proxies, namely, for instance, the Donster-Waradan formulation of the mutual information, or the Wasserstein distance. So we show here the results for the Ising model and the OU process. Where the new methods, so Donster-Waradan is shown here in blue, and the Wasserstein in black. So here, well, we can see that actually JSD still performs better than the other methods. And if we just compare all of them, we kind of liked perhaps the distance correlations a lot. Perhaps the performance wasn't always the best, but it was about 15 times faster than the other methods. So there is like a computational benefit. Okay, so I reached the conclusions. So I started my talk with two characterizations of the sufficient statistics. One was like the classical Fisher-Neyman factorization. And the other one, which was important for this talk, was this characterization in terms of mutual information. This kind of perspective of sufficient statistics led us then to variational characterizations, namely that sufficient statistics can be seen as information maximizing representations. This then led us to learn approximate sufficient statistics using proxy quantities of the mutual information. We used the learned statistics to boost the performance of two rather different approaches to Bayesian inference with implicit models, namely sequential ABC, or SMC ABC, and sequential neural likelihood. So we like the approach because it kind of plays well with others. So it can be used to enhance existing algorithms, which we hope is thus useful for many people. So for more results and also for more comparisons, I refer you to the paper, and we also have a code available using on this link for those of you who want to try it out in practice. Thanks a lot for your attention.
Okay, thank you very much for your interesting talk, Michael.
Thank you.
Do we have any questions? I've seen there's a couple of raised hands. So, Michael, Michael Beister, do you want to go ahead and ask a question?
Sure. Yeah. Thanks a lot for the talk. It's really cool work, I think. I have a question because you mentioned that if you maximize the mutual information via the JSD, then it's basically equivalent to getting the ratio of the joint and the marginals. And I mean, in principle, you could just use this ratio to directly sample the posterior with MCMC. So I'm wondering if you compared the SNL approach to just doing that and basically not doing SNL anymore, but just directly sampling the posterior.
Yeah, so this is kind of what we did in that early work. So where indeed we used this kind of approach to learn the ratio. And then some years later, people kind of used more neural network type of approaches to do the same thing. And yeah, we have a comparison in the paper. So in our work, we called it likelihood for inference by ratio estimation. Then the work here, they called it neural ratio estimation because they used a neural network or deep learning. And we have a comparison with that in the paper.
Cool, thank you.
And Gail has a question.
Yes, that's really interesting and very nicely presented as always, Michael.
Thank you very much.
I've lost track of what's happening with the dimension of the sufficient statistics because, of course, we have this trade-off, don't we, between the dimensionality of the sufficient statistics and their informativeness, and they pull against each other. So, I mean, the results you presented all look very positive, but do I have something that tells me that, you know, what you're gaining in terms of the informativeness is not harming us in terms of computational accuracy, because you're at the same time to get the informativeness, you're increasing the dimension of the summaries?
Yeah, so thanks a lot for the great question. Yeah, I think this is really one of the key open questions that I see in this approach, like which I try to discuss here a bit. How should we choose the dimensionality of G? Yeah, so there will be a trade-off between computation and information gain, and also at one point I imagine actually that also the statistical performance goes down because we have to approximate or learn more complicated functions if the number of statistics that we learn is larger. So I would say the first thing that one could do is, because we have two objectives in our variational formulation, right? So either this one here or then the distance correlation, that one uses some kind of like validation set approach to choose the dimensionality of G, or perhaps parameterize a function with higher dimensionality, or like output dimensionality, then but put a regularization constraint or penalty on the number of outputs, and then choose the dimensionality via cross-validation. Because we can generate data from our simulator, if the simulator is not too expensive, right, we can actually do that. But yeah, would just be my first try. Whether one could do something smarter, yeah, I'm sure. But yeah, I'm not quite sure how to do that.
Okay.
And there's a question from Umberto in the chat. Umberto, maybe you might want to give some more details about this figure.
Yeah. I was talking about slide 22. There is the rightmost figure I didn't quite get what it represents. Thanks.
Okay, so this one, right, where we plot the true sufficient statistics versus the learned one. So ideally, what we want is just a diagonal line or some kind of affine transformation. So, and in a sense, right, the curve in black, which corresponds to the one that we learn with our approach, has this kind of like affine behavior. So this would mean that if the true sufficient statistic changes, ours changes as well, just up to a some kind of scaling constant, and the relationship is also like linear or approximately linear. And this is kind of what we want, right? So in a sense, the scaling and the swap sign, the algorithms don't really care about that, right? This can be compensated by either the SMC ABC or the SNL algorithm. So in that sense, we are happy with the black curve. We wouldn't be quite happy with the red curve. The reason being is that if the sufficient statistic changes, so if aspects in our data change, we can't see that in the learned statistic, right? So what this then would mean is that, yeah, I suppose that it's less informative for the estimation of the parameters, making perhaps the posterior broader, I guess, and just in general less accurate than when we have a relationship as here in black. Is it now clear, I wonder?
Yeah, I mean, I was confused of the fact that I was expecting, of course, an increasing black relationship, but now you clarify that, of course, the sign doesn't matter here, and that's all I need to know.
Okay.
Thanks.
Good.
Thanks so much.
We have a question from Petr Jovanovski.
Thank you, Michael, for the nice presentation. I have had a chance to.
Let me have to increase the volume on my side, or could you speak a bit louder?
Can you hear me now? Well,
barely, but I think it's better. Yeah.
Let me see.
That's better.
That's good.
Okay,
Yeah.
now it's better.
Yeah, thanks.
I also had a chance to play with the software, which is also easy to use, so one can get some results immediately. But I have a question. If you could go to the slide with ABC SMC.
The algorithm slide.
Yeah.
Okay. Yep.
Okay. So in ABC, what one usually does is the observations are summarized, and then what we infer is the density of theta given the summary of the of the observations, and that's the summary of the observations is fixed.
Yeah.
But in this case here, we update the neural network at each round, so we also get a new summary of the observations.
Yeah,
that's correct.
That's correct.
Yeah. How does one reconcile that fact that we need to do posterior inference on a fixed, on a fixed data set, but in this case it is changing?
Okay, yeah, so our solution here was quite simple, but your question actually makes me think of one could do it perhaps actually better. So what we do is quite simple. So just in each round, we just use the updated network, and that's our new summary statistics. So we forget about the past kind of network. So we only have one S0 here, for which we then approximate the posterior here. Now, so in a sense, the networks and the learned statistics from the previous round, we don't use them in here when we approximate the posterior. But so that's what we did here. So, but perhaps your question points to the question whether actually it would make sense to perhaps actually use perhaps some of the other statistics as well. And yeah, one could try it out whether this would make sense. So I think the cost is right that we are conditioning on more dimensions or on a larger vector. And that's what we wanted to counteract in the first place. So to work with lower dimensional representations. So that's kind of like the price that one had to pay. A possible benefit could be that, that perhaps in different rounds one looks at different aspects of the data, which may make the approach a bit more robust. But in a sense, so here we don't see much improvement over the rounds, but perhaps here, perhaps here we see it go slightly up. And I don't know, this is now just, because of the variability, it may not be significant. So whether this approach that your question hints at could lead to perhaps smarter things where you kind of perhaps combine the learned statistics from the previous rounds in yet another network, perhaps. That's kind of my long answer to your question. I hope it helped a bit.
Yes. Okay, thank you. So the summary statistic stays fixed in the round, and then in the next round it is updated. So in a way, here we augment our data set with the new samples that come from a new proposal distribution. So it's the data in D comes like from a mixture distribution.
And that's why we have to correct here with the mixture of all the proposals. But then we only use a single S just from the current round to obtain the posterior estimate at the current round.
Okay, okay, it is clearer now. Thank you.
So yeah, thanks.
So, Michael, a related question is, do you think there's any danger of, or let me say it in a different way, do you think it's possible to show that this algorithm has any convergence guarantees? Because there's changing the summary statistic function as you go through could create some sort of instability.
Yeah, one would hope that one could piggyback on the existing convergence results of the underlining on algorithms, because yeah, so I mean, a simple way, right, to ensure convergence is just to freeze the learning of the network at one point and then just continue with the standard algorithms, right? So in that way, one could kind of, piggyback on the existing results, I suppose perhaps the theoretical approach for any proofs could be that one had to show that at one point the learned statistics kind of stabilize, which I think needed to happen anyway for the algorithm to work properly. And then perhaps the proof would be, we assume just a delta change in S, and then we would see what the consequence of that is in the existing convergence proofs.
Okay, brilliant. Does anybody have any final questions before we finish? Okay, in that case, oh, sorry.
I woke up just now with another question. Sorry.
Yeah, go ahead.
Yeah, I mean, Michael, I mean, in the end, you use several kind of distances or metrics to compare distributions. And I think that, as you suggested at some point, freezing the learning, I mean, can't it somehow be done sort of easily using one of these divergences measures?
Yeah, it could be, right? Yeah. So, I mean, also, right, in practice, we wouldn't, this plot in a way, one can't just, so, okay, so we wouldn't have the ground truths available, but indeed, one can't just compare the two, indeed, and then just stop, for computational gains. Absolutely.
I'm not sure if it's just for computational gains, meaning that, I mean, from the methodological point of view, we are, as Peter suggested in his previous question, we are in standard SMC-ABC, for a varying threshold, we are having several approximations to a certain posterior that is determined by a specific observed summary statistic. And in this case, instead, you're always changing somehow the underlying observed information. And again, then we have and I'm not sure this is really understood what it is.
I mean, the theory, I think one can make a theory paper out of it, right? So, I mean, the key thing is that the S may not change, it's kind of, we continue the learning with more data. So it's not like we restart from scratch. So the theory, perhaps a bit like, as in my answer to Dennis, so I think the change in S can be bounded as we go in our rounds. And then, I think that's perhaps something for us to think about. What is the change in epsilon as in standard SMC versus a small change in S, right? So in that sense, I wonder, whether mathematically the two things are actually could be like handled via similar tools. Does that make sense?
Yeah, it's a very interesting research question, I think.
Right. So you could say the distances between SI and S0, you kind of just expand them. You say well, we have like we just make a like using triangles like inequality kind of. We smuggle in the S from the previous iteration, and we would assume that we only have a small change, right? So then we have like, we could think of a noisy perturbation of the summary statistics. And I mean, I think there is some old work by Watham, is his name, right? It's from Imperial College, that I think looked at this idea of the stochasticity of S as well, or also considering like epsilon, the threshold in ABC, to be a random quantity. So perhaps the theory from there could be useful to develop a theory for this kind of algorithm here.
What's the author name? Sorry, Michael?
Yeah, I have to Google it.
Ollie Ratman.
But
Yeah,
doesn't it enter also into Noisy ABC by Richard Wilkinson and so on?
Exactly, yeah. Maybe somebody could post the name in the chat.
I think a version of this paper is in the Handbook of ABC.
Okay. Oliver, I think his first name, yeah. I'm not quite sure how to spell his family name.
Yes, no, me neither.
Okay, now I get it. Okay, I think. Yeah.
Oh, great. Great.
Good.
So, would anybody like to ask any final questions to Michael? Okay, in that case, thanks, Michael, again, and thanks everybody for coming and for this nice discussion we've just had.
Thanks.
And see you next time. And I'll stop the recording now.
Thank you very much.
That was great. Thanks, Michael.